Welcome back to Linear Algebra. Today we're going to talk about elementary matrices, invertibility, and finding inverses of 3x3 matrices and bigger. So, what is an elementary matrix? Well, before we had row operations, and turns out these row operations we had are transformations, so they can be written as matrices. So for instance, if I give you a matrix A, B, C, D, E, F, G, H, I, it's 3x3, I can write a matrix that scales the third row by 2. So if you remember the identity matrix, so it has 1s in its diagonals and 0s in the rest, well, this just takes one of each row and returns it. So if I want to scale the third row by 2, I just take the last one and I make it a 2. And if we do some matrix multiplication here, our end result is going to produce, so we have A, B, C, D, E, F, and then we would get 2G, 2H, and 2I. So that's when we multiply this by A, so I should put an A there. Okay, so that is the elementary matrix that scales the third row by 2. So I'm going to show you a few examples of the operations and then how we get our matrices. And not only that, but because these row operations are invertible, we're going to know that these elementary matrices are invertible as well. So let's take a look. What does E4 do here? And what operation is this? What is this row operation? So we have 1s in all the diagonals, so it's leaving the rows alone. But we see here, we have this -4 here. So this elementary matrix represents R3 is now becoming R3 minus 4 of row 1. So this is in the first column, so it's going to deal with the first row. And in the third row, so it's dealing with the third row of our result here. So how do we do the inverse? Well, for our inverse, what we want is we want R3 to become R3 plus 4R1. So we want to take it back to where it was. So this inverse is going to look like, well, we have 1 in our diagonals, and then instead of a -4 for our bottom left, we're going to have a +4. So that's going to take our row 3 and add 4 of row 1 to it. So it's going to be invertible. So we can call this E4 inverse. Okay, E5 inverse. What is going on here? Well, this looks just like the first matrix we did. It's going to scale row 3, or sorry, it's going to scale row 1 by 3. So R1 becomes 3R1. So what do we do for the inverse? Well, we want our R1 to become 1/3 R1 because we need to get it back to its original. So for that, we just put a 1/3 here. And we're done. So this is E5 inverse. And you can check yourself that this works by multiplying the two matrices together, and you'll get the identity back. So for instance, if we take a look at E5 times E5 inverse, for our top left entry, we're going to get 3 times 1/3 plus 0 times 0. So that's going to be 1. We're going to have 3 times 0 plus 0 times 1. Then we're going to have 0 times 1/3 plus 1 times 0. And then for our bottom right entry, we're going to have 0 times 0 plus 1 times 1. So we get our identity matrix back. And that was just using the multiplication rules we learned in one of the previous videos. So what is this E6? What does this represent? Well, this is a row swap. So this is row 1 swapping with row 2. And you can tell depending on which position the 1s are in. So the 1 is in A12 and A21. So these means that these two rows are switching. So what's the inverse? Well, the inverse is just going to be switching the rows back. So we had row 1 go to row 2 and row 2 to go to row 1. So we want to switch those back to normal. So essentially, the inverse matrix is exactly the same in this case. So we get a 0, 1, 1, 0. So these 3 operations are the only 3 operations we can do. And we've showed with specific cases that these work. With more general cases, for instance, I could change this -4 to a -c, and then in the result we get a c there. Again, we could just do For instance, in E5, we could do C, and then we do 1 over C. And of course, with the row switching, we could pick any two rows. So these generalize very, very easily. So we can see that this is going to be true for all of our elementary matrices, for our row operations anyway. Okay, so that is an elementary matrix. Each elementary matrix does only one operation. We will never have an elementary matrix that does more than one operation. So, that being said, here's how we can use these elementary matrices to find the inverse of a matrix. So, if we have a matrix A, and we have a matrix that is the identity matrix, if it's invertible, we can do a bunch of elementary operations on A to get back to the identity matrix. So, that means that if we can take the identity matrix, whoops, these are backwards. If we can take A to the identity matrix, then we can take the identity matrix to A inverse. So these operations will be exactly the same. So here's the proof of it. So this is an if and only if statement. So we need to show both ways. We need to show that A can go to IN, and then we need to show that IN can go to A inverse. So here's what we're going to do. We're going to suppose that A is invertible, just for the sake of it, because we need A to be invertible for this to work. If it's not invertible, then clearly it won't have an inverse, so what would be the point of the theorem? So suppose A is invertible. What do we know about inverse matrices? Well, we have that AX is equal to B has a solution for every B. And this was just one of our definitions that we learned earlier, or sorry, one of our theorems that we did earlier. So if you remember from the beginning of the course, this means that there is a pivot position in each row. Okay, so here's a question. If A is invertible, what's the size of the matrix? Well, the matrix has to be square, right? And if it's square and there's a pivot position in each row, well, that means that we can get to the identity matrix. So we see there's a pivot in each row, and it is reducible, there's a solution, so therefore we can get A to go to the identity matrix. Okay, so we've proven that we can get A to the identity matrix. Now we need to prove that we can get this identity matrix down to A inverse. So let's go the other way. So we want to assume that A is going to be reducible to the identity matrix. So we learned just previously in this video that we can use these elementary matrices to represent our row operations. So A goes to A goes to the identity matrix through these row operations, which means that if we take A and then we left multiply it by the matrix E1 and then we do it E2, if we keep multiplying like this, eventually we're going to reach some final elementary row operation, which we'll call P, that takes us to the identity matrix. So this is the list of elementary row operations that takes A to the identity matrix. So we can rewrite this a little bit differently, and this will help us. So we can take A, and then we can group all of our EPs together. So EP minus 1, all the way to E2 and E1, and this will equal the identity matrix. So what do we learn about elementary row operations that can help us here? Because we want to get an inverse out of this. Well, we learn that all of our elementary matrices are invertible, which means that we can take EP minus 1, all the way to E1, and if we take the inverse, along with the original elementary row operations multiplied by A, this is just going to equal EP inverse, all the way down to E1 times the identity matrix. So, of course, what we see here is that this will become the identity matrix, and we'll be left with A. And then on the right side, we'll just be left with EP minus 1, all the way down to E1. Oh, and this should be inverse. I forgot the inverse there. So this is important. So what we're saying here is that A is just equal to the product of all of the elementary row operations inverse. Okay, so this is useful because we know that A is invertible, right? We're assuming that A is invertible here. Therefore, if we take A inverse, it's just going to be the inverse of all of this. So we take this, our product of elementary matrices, and then we take its inverse. And what do we get? We just get the original product of elementary matrices. So what does this tell us? This tells us that A inverse is just equal to all of these elementary row operations as matrices. So this is the same thing as EP minus 1, E1 times the identity matrix. So if we take a look here, let's take a look at this. The identity matrix is equal to all of these row operations times A. And the inverse is equal to the identity matrix times all of these row operations. So we have that if A goes to IN, then simultaneously IN goes to A inverse with the same operations. So the same order of operations. So we have a proof here that if we take A to IN, the same steps are used to take the identity to the inverse. So how do we use this? Well, we have an algorithm for finding it. So what we do is we attempt to row reduce the matrix containing A and the identity to the matrix containing the identity and the inverse. So essentially, this A goes to the identity, and simultaneously, if we do the same steps on the identity matrix, we will end up with the inverse. And this is because the sequence of steps on A is the same as the sequence of steps for the identity, and it takes them to those matrices respectively. So I know I've repeated the same thing a few times, just trying to drill this in, because on an exam, this is one of those things you forget randomly, and you're like, how do I do it? And then you come out of your exam and you'd be like, oh, right, I do this really obvious thing that I should have already known. So let's do an example here. Here's A. We want to find A inverse. So what we want to do is we want to set up our matrix to include both A and the identity matrix. So we're going to have 1, 0, -2, -3, 1, 4, 2, -3, 4, and then we'll just throw the identity matrix beside it. So remember, the identity matrix should be the same size as your original matrix. If your matrix A is not square, this won't work, so keep that in mind. Okay, so just for clarity's sake, I'll put a line here, and I'll write that this is A and this is the identity, just so we can see how things change here. So we have to reduce A to the identity matrix. So what we'll do is we're going to clear up the first column. So we're going to keep the first row the same, because the one there is okay. I'll put the line in blue, just so I don't have to switch colors. So we're going to add 3 of the first row to get rid of this -3. So -3 plus 3 is 0, 1 plus 0 is 1, 4 plus -6 is -2, and then we have to do the same thing for the rest of our row. So 0 plus, 1 plus, how do we do this? 0 plus 3 is 3, 1 plus 0 is 0, 0 plus 0 is 0, and then for the third row, we're going to subtract 2 of the first row. So 2 minus 2 is 0, -3 minus 0 is -3, 4 minus -4 is going to be 8, 0 minus 2 is going to be -2, and we're left with 0 and a 1. So we can kind of see our elementary matrix coming into play here. So this second row says that we've taken row 2 and we've added 3 of row 1, which is what we did. And this third row says we've taken row 3 and we've subtracted 2 of row 1. So this first step, we can clearly see the elementary matrix at work here. This is going to get muddled up in just a second, though. So our first column is fine. So now we need to work on the second column. So 1, 0, negative 2, this still looks good here. We can keep that the same. 0, 1, negative 2, the second row looks good. We can keep that the same. And now we want to we want to add 3 of the second row to the third row. So we have 0, 0, we're adding negative 6, so we get 2. Then we're adding 3 to the second row, so negative 2 plus 9 is 7. We get a 3 there, and we get a 1. So now the elementary matrix isn't really showing, and it's kind of confusing as to what we did, so it happens. Okay, and now we have to work on the third column. So this entry right here needs to become a 1. There's a pretty easy solution to this. So we're just going to add the third row to the first. So we're going to get 1, 0, 0, 8, 3, 1. We're going to add the third row to the second. Get 0, 1, 0, 10, 4, 1. And then we're going to divide the third row by 2, so it becomes a 1. So we're going to get 0, 0, 1, 7 halves, 3 halves, and 1 half. So here we now have the identity matrix, and this should be A inverse. So you can check this by multiplying. So if we take A and A inverse, we should get the identity matrix back, so you can double check your answer like this. But for the sake of keeping the video short, this is your final result, and you can check this on your own to make sure the inverse is correct. So that's it. If you have any questions, please leave them in the comments below, and I will answer them as soon as I can.